Hi, my name is Izzy Bremner. I'm from a school, and this is the JYPT example presentation, pulling glasses apart. The problem states, put a thin layer of water between two sheets of glass and try to separate them. Investigate the parameters affecting the required force. So, to start off, a capillary bridge is the minimized surface of a liquid or membrane created between two rigid bodies. However, it can happen between two liquids as well. The presence of the bridge, depending on its shape, can cause attraction or repulsion between the two bodies. And this is one of the main effects taking place that I'm going to go into in more detail very shortly. So, going through some of the conceptual theory. So first, initially, we've got some water, we've got some glass on top, and it's just not moving, it's at equilibrium point. The internal pressure is slightly larger than atmospheric in order to support the weight force of the glass. And yeah, so we've got an equilibrium here. Then we pull on the top sheet of the glass in an attempt to separate them. When the top sheet of glass is pulled up, a capillary is formed on this water-air interface. And if we look at the forces acting on a single molecule of this surface, due to the curvature of the surface and the surface cohesion forces, we get these forces, which has a net inwards component. So, if we look at that happening all on the surface, again, we get some forces cancelling out, and a net inwards force caused by surface adhesion. So this causes a movement out by this external surface of the water, which decreases the internal pressure until it's less than atmospheric, and then you end up with a force due to a pressure difference acting inwards, so we end up with another equilibrium after that initial motion has taken place. So at this point, we still want to know the force that's required to pull up the top sheet of the glass. We've been working in a different plane. So again, we've got atmospheric and internal pressure. As the internal pressure is less, we've got a force due to the difference in pressure, which means there's a net force acting on the top plate, which means that it requires more force to separate it from the water in the bottom plate. So capillary action is the reaction of surface adhesion and cohesion, and this effect is where the equations that I'm using will come from. So this is the Laplace-Young equation, and it's for the pressure inside the capillary of a capillary action tube, and it includes the radius of a round tube, which complicates things as we aren't using a round tube, but we just put thickness in instead. So to go into experimental, this was my experimental setup. I had a force meter, I had some glass, some water, another sheet of glass, and then I would pull up above the force meter in order to separate those two sheets of plates of glass. So these are the parameters that I tested. The first one that I'm going to talk about is water volume. And so as we couldn't use that theoretical formula in order to calculate numbers, however we can still use it to look at proportionalities and trends. So looking at this theoretical formula and wondering what increases or decreases when I increase or decrease water volume. So at a low water volume, the water doesn't actually cover all of the plate of glass. So we end up with a decreased area that this pressure difference is acting over in order to cause the force. So with a higher volume, you end up with an increased thickness and therefore a lower force needed. So we're expecting here that there'll be sort of an optimum trend where you'll have the most force required and then decreases on both sides of that due to the two competing forces that I just discussed. So, and you can see that in our testing, this is exactly what we got. We got an optimum here, and an increase up to it, and a decrease out from it. And so you can see here that this is an example of the decreased area covered by smaller volumes of water. So normally it would cover this like whole square, and it's not, so there's a decreased surface area that pressure difference can act over, resulting in a decreased force. And we've also got a bit of a plateau here at the end, which I believe is due to the fact that after a certain point you're putting water on, you put the glass on top, and the excess water just squeezes out the sides. So you're not actually changing water volume from that point on, it's the same water volume, so you're going to get the same force needed to pull up that top plate. So now going into surface tension. So we thought surface tension was important because it's in our equation. So you can see here that it's multiplied in the equation. So if you increase surface tension, we would expect an increase in the force required to pull up that top plate. So you can see here that when we lowered surface tension, it definitely appears to be much lower than when we did the test with just water. And then we decided to go through uneven lifting. So before we had 4 points on our plate where we had like strings tied in order to lift up centrally. However, in this case, we untied 2 of those strings, so we lifted it from just one side to see if we can see if lifting from an angle decreases that force, as it's going to change the way the pressures in that capillary work. So if you're looking at it, this has actually ended up being within error, and so yeah, not quite sure what that's about. So going back through my theory again, when the top sheet of glass is pulled up, a capillary is formed on this water-air interface, and this is the forces due to cohesion on a single surface molecule, which has a net inwards force, and this acts along the entire surface, resulting in an overall net force outward, which causes a movement outward, and then that results in a lower internal pressure when compared to atmospheric, which creates another equilibrium as those forces balance, so we get no more motion, and then that pressure difference acts on the top sheet of glass, which causes the force required to pull up that top sheet of glass to increase due to the net force acting down on the glass. This was my mathematical model, and to conclude my parameters, to get the effect on the force was that there was an optimum at 150 microliters and a decrease with surface tension. These are my acknowledgements and my references. Thank you very much.
Hello, my name is Finnegan Messley. I'm from this team over here. Got a few questions for you, Izzy. Firstly, how many repeat tests did you do?
I did 3 repeats.
Cool. Could you please define cohesion and adhesion?
So cohesion is the tendency of similar particles to attract or stick to each other, and adhesion is the tendency of dissimilar particles to stick or adhere to each other.
In which case, could you please go to slide 13? You said the force was due to adhesion.
Oh, that was my mistake. It's actually due to the cohesion, as this is due to the bonds between the water molecules on the surface to each other, and other water molecules within the fluid.
Could you please define surface tension?
Surface tension is the tendency of water to minimize its surface.
Could you please go to slide 28? Would you claim that there is a trend here between surface tension and
it's pretty obvious. I'm not sure there is quite significant error in my testing, but it was in our equation, so I'm assuming that it would be lower.
And can you please go to slide 30? Cool, awesome, thank you. Just going back to 28 with your graph, you said low surface tension. How did you achieve the low surface tension?
So I added detergent to the water.
Did you measure the surface tension at all?
No, sorry.
How did you measure the small volumes of water?
I used micropipette, one of the mechanical ones.
Hello, my name is Finnegan Messley, and I'll be opposing Izzy Bremner's pulling glasses apart. Firstly, I'd like to thank Izzy for that great presentation. In terms of addressing the problem, I think there are 3 key things that you really need to do. The first one is to actually achieve the phenomenon, which I think she did really well. The second is investigating relevant parameters, and I think she did this with some success. Some of the parameters she investigated really well, and some of them were extremely relevant. I feel like some of them could do with some more investigation, and also some of the others, there were some parameters that she could have investigated, I think that she should have. In terms of strengths, Firstly, I really like some of her explanations in terms of the capillary bridge. The force diagrams were really helpful for the understanding of the problem, especially with your pressure explanation of the phenomenon. I also liked that you started to use the Young-Laplace equation. I think that is probably one of the best ways to go for modelling this problem. I think you could have taken it a bit further, and I think there's some problems with how you used it, but we'll get into that in a bit more in the discussion. So overall for your model, I feel like there's a little bit more you needed to do to get it working properly, but we'll get to that. In terms of experimental strengths, some of the parameters she investigated were really relevant. For example, water volume and surface tension. I think those two are really key for addressing the phenomenon. The uneven lifting, I was a little bit unsure about. One, I don't think it's the most important parameter. I think there are other parameters, for example, plate area, that might be more important. And also, she didn't seem to have, she didn't really seem to have any idea of what was actually happening for that one. Maybe we'll get into that in the discussion. In terms of negatives, as I said, the model needed a bit more work. Experimentally, I believe she just lifted it up with her hand. She didn't really explain her setup that well, but I think that's something she could definitely improve on, is the lifting mechanism. And as I said, testing some different parameters like the plate size. She also claimed some trends when there didn't really seem to be any, which is something we might get to in the discussion. There was also quite a lot of error in some of her measurements, and I'd like to talk about sort of where that comes from and how she might have minimized it, because she didn't seem to minimize it very well. So in terms of discussion points, first thing I'd like to look into is some of the maths she used, sort of how she could go about applying it a bit more in some of the problems that she had with it. Firstly, she used, I think, the thickness, like the height of the different plates instead of the radii, which she should have been using. And there's some relationship between those two that I think she should have looked into. Next, we'll talk about her experimental method, because it wasn't particularly clear from the presentation. And so we'll go into that a little bit more and how she did it and what sort of the advantages and disadvantages of her method was. Then I think there was one key aspect of the problem she really missed, and that was correct flow between the two plates, because you can't, it said separate the plates and you can either lift it or you can slide it. I think. Okay. And so now I'd like to invite Izzy up for a discussion. Firstly, your mathematics. Can you please go to your mathematics slide?
This one?
Yeah, sure. Start with that one, because there are two different ones, which I think was also confusing. So firstly, could you explain what the differences are between the two models that you showed?
So for one thing, this one is talking about pressure, whereas the other one's talking about force, and that's a simple multiply by area.
Okay, cool. Yeah, that makes sense.
And the other one is that this one talks about thickness instead of the radius of the capillary tube.
Right, so why did you decide to go with thickness instead of radius?
Well, in this case, we don't have a capillary tube, so to say. So these are about, those equations are for capillary action, which is very thin tubes and water adhesion acting to bring water up them. But we don't have a tube, so to speak, but we are still forming a capillary. So I figured that the radius was about thickness, or at least proportional to it.
That I might agree with. So if we look at what's actually happening on the two, so for a tube, what that model is typically used for, I believe, is the case like you illustrated here. We've sort of got the same radius here.
A tube with a small radius.
Yeah, in both directions as well, so coming down the page is also the radius.
Yes.
But what you have in your experiment, this problem, is we first,
Yeah.
And so we've got this one radius here, and you're saying that that should be roughly equal to the height?
Yeah, I think that it would be proportional at least, and therefore that we can use the equation like you said. That I didn't compare numbers directly, so therefore we should be able to compare at least trends from the equation, which is all that I used it for, which I think is perfectly valid in this case.
Yeah, but I don't think you really backed that up with any real physics. So if we actually have a look at what's going on, would you agree that regardless of what's happening, this angle here between where the water meets the glass meets the air, should that be constant or should it vary?
Where the water meets the glass meets the air. In this case, yeah, it would be constant. So if you like zoom up, because that's a contact angle which is defined by hydrophobic and hydrophilic surfaces, which is a separate thing to this capillary forming. And so you actually would sort of end up with something more like that.
Yeah. And so you do have a constant angle here. And so if we assume this is a circle, I think if you actually looked at it a bit more closely, that if you increase the height, and this angle stays the same, and you assume that it's a circle, that it is actually proportional like you're saying it is. But I still don't agree that, wherever your model was, I don't agree that that's correct, but I agree that it shouldn't really have an effect the way you're using it.
Yeah, so I think that it was perfectly valid to take the conclusions that I took from those, from this equation.
Yeah, but I don't think that is the correct maths completely. I think you're missing out a bit here, but I think we should move on.
Right.
So the next thing was your method. So can you please explain to me how you would go about doing your experiments?
Okay, so in this picture here you can see a micropipette, which is just mechanical. You set the number by turning the dial, and it automatically pipettes a specific amount of water. And then we've got a larger glass plate, which I would pipette the water onto, and then a smaller glass plate, which I would put down over top of it. And then using the force meter, using these strings above the force meter, I would pull it up in order to, and then the force meter being plugged into a laptop, which would measure the required force for those plates to release.
Okay. Firstly, I think use of micropipette is really good. It gives you really accurate measurements, and so I really agree with that. But something I'm concerned about is that pulling it up by hand, how do you ensure that it's actually pulling up flat? Like pulling up purely horizontal?
In this case, the main way of ensuring that was using the fact that it was tied on all four corners.
Yeah.
And so I also thought that the fact that I then tested uneven lifting would sort of, and it didn't really make a significant difference, shows that it's not going to make a massive difference to my testing, the fact if I wasn't pulling perfectly straight, because it was within error on this graph. And so it doesn't make a massive difference, like, because this was over-exaggerated, well past what I would be able to do normally.
Yeah, so how much lifting to one side was this graph from? Because it just...
So this was purely lifting on one side.
Okay.
So all of this force was being applied to one side of the glass plate. So it was like fully lifting like that.
And it's not different with an error?
No, it's not.
Okay.
Yeah.
But you're getting like completely different radii from that, but also one of them matters.
Well, I think that, like, with this especially, you start getting a lot of different effects happening because you start getting water flow, which brings in a bunch of different weird effects that you get when you have thin layers of fluids and water flowing. Microfluidics, I think it's called. But I think that it can be reasonably explained by going very deep down that rabbit hole, but I didn't.
I think that's fair enough. And I think your experiment, while not perfect, I think is good enough for the testing that you did. And I think I would like to see you work more on some different parameters first rather than going more in depth into your setup. So I think that was good for the most part. Now I'd like to talk about Couette flow rather. So you lifted it up, right?
Yes.
Did you ever consider it separate? So you totally could have just like slided it, right?
Well, for one thing, experimentally measuring those forces would have been a bit more difficult because you don't have a direct line up to a force meter and going, but no, I didn't consider that. But I think that I fully fulfilled the problem. I tried to separate two plates and I measured the required force. So
okay, but I think this is like a really important side thing. So if we look at...
I don't think something can be really important and a side thing.
Alright, we'll just go with really important, right? So we can actually and it's really easy to analyze mathematically. So if we look at a cross-sectional here...
I'm not sure I would go
I'm going to stop this one at this point, because this is obviously something that he's looked into that was not mentioned in the presentation, and this is something that is going into some of his own material, so I think we've got to move on to another point.
Alright.
Also, I know that it's one of the easily solved Navier-Stokes, and I don't want to.
I've got another point here somewhere. Maybe?
Time's up. Okay.
Firstly, I'd like to thank Izzy for that good discussion. It's good fun. I think the first thing we talked about, I think the most important thing, was her mathematical modelling. I think she was on the right track, but had made some assumptions that I didn't agree with, and while they didn't really affect what she had done because she never actually applied her model numerically, I think it would have been important to investigate the relationship between the angle and the thickness, and also the fact that she used two different equations and sort of didn't explain those.
Oh, sorry.
Thank you. We then talked a bit about her method and setup. She didn't really go over it in that much detail in the presentation, and I think it was good for the most part. She used a micropipette to accurately measure the volumes, and she lifted it up by hand, which I don't think was the best way, but I think within all the other error from all the rest of the setup and everything, I think that was good enough for now. And then we were about to talk about some separating versus sliding. I think it would have been really interesting for her to look into that. Thank you very much.
So first off, as I'd like to thank Finn for that discussion, that was a really good time. The application of the two mathematical approaches, we discussed me just putting thickness in instead of radius. We disagree on how that was applied and whether or not that was reasonable, but I think that the definition of making an assumption is approximating something that doesn't end up significantly impacting how you use it. So I think in this case that it was perfectly reasonable for me to apply it in the way that I did. If I directly compared numbers, that might have been a different scenario, but I didn't. We discussed the variation of lifting by hand, and we agreed that the variation was probably not significant in my setup, and that it was reasonable that I did that within my setup. And I do agree that perhaps that is something that I could have gone into a little bit more detail in my presentation. We also started to discuss co-wet flow, but as I didn't bring that up in my presentation, and I did fully fulfill the problems as I tried to separate two sheets of glass and investigated the required force, that it wasn't something that was really relevant to bring up in this case. And I'll just quickly run through my conclusions again. So we have a net force acting on a single surface molecule, which acts along the entire surface, which causes the net force, which causes a movement outward by the water-air interface, which causes a lower internal pressure, which creates an equilibrium, but that pressure difference then acts on the top plate, which creates a net force acting downward, which increases the force required to pull up the top plate. This was my valid mathematical modelling. And the conclusion for my parameters was that water volume has an optimum at 150 microlitres. You should decrease your surface tension, and that uneven lifting does not have an impact. Thank you very much.
I have a super brief, unimportant one. Can you just quickly label thickness on the diagram behind you?
Yes. The thickness would be the distance from the top plate to the bottom plate.
Finn?
Yep.
Why is radius vertical there on your diagram?
So what we're talking about when we're talking about radius is as if this curve was a circle, and this is actually should be much shorter, but it's the radius of what that curve would be if it was a circle.
Oh, okay, so it's just a bad 3D diagram.
Not really. You can see it's a circle.
Okay. Thanks.
Low surface tension. How low was the surface tension?
Well,
Did you measure it?
no, evidently not low enough to make a difference. Yeah, we didn't measure that, sorry.
Is he keeping a slide 11, please? Is that a net inward or a net outward force?
Outward, I would say. Outward, yeah. The water moves outward. I mean, it depends who you define your vectors.
Izzy, you were talking about sort of that, and then you pull it upwards and you get the change. Did you measure the force, I guess view the force as the force changed? Did the force change while you were lifting the plate?
If you mean like that initial pull to create the capillary.
And then onwards?
Yeah, so it's pretty much a steady increase. I didn't go into it in my presentation because it's pretty boring. It just sort of increases until the plate pops off, and I just measured the maximum.
This is a little bit unusual. This usually doesn't happen this way. Does only water have a surface tension?
No.
So other things have surface tension?
Yes.
Is that what this is?
She said surface tension was the tendency for water to stick together. I'm glad the opposing team is being so helpful.
Yep. More just as an example of things that we look at for everybody. Can you go to slide 26, please? Okay, no, there's a graph for me there somewhere.
Okay. This one.
That's the one.
This is the one.
That's the one. What's your explanation for the second peak that's occurring near 1,000, that could be occurring near 1,000 microlitres given your error bars?
I don't think that there's really a peak. I would say that those were all within error, which is where I was talking about the kind of plateau that occurs where you sort of get, you put the plate on and excess water squeezes out. So,
And
Yeah.
the question I would ask about that, when I sort of wrote it down, was, did you observe that the water squeezed out?
yeah.
Yeah.